Okay, we're picking up with lesson 3 of unit 5 in the middle of the notes on the back of the second page, I believe. And we're going to look at, in this video, how the graphing calculator can help us write the exponential function. It's going to be called an exponential regression because we'll be finding the best possible equation that the calculator is capable of finding based on the data that we enter. So I have the steps here. You can see that on the Inspire there are quite a few more steps. Desmos is much quicker as usual. So pause this video to jot these steps down before we proceed so that you'll have these handy. I'm going to go ahead and move on to our example problem here. It says a pharmacologist is testing a new antibiotic. At the beginning of the first day of an experiment, there were 2,500 bacteria in a culture dish. At the end of the day, the number of bacteria present in the dish was recorded in the table below. All right, so I suppose this is showing day 1, day 2, day 3, and on day 6 there are only 800 bacteria present. So based on the data in the table, is this an example of an exponential growth or decay? And I would say that as the days increase, the number of bacteria decrease, then the number of bacteria would be decaying. So I would say that this is a decay. And it says explain your answer. So I'll just say because the number of bacteria decreases over time. Using the regression capabilities of the graphing calculator, find the function f of x equals a times b to the x power that models the data in the table. So let's look at how we would do this using both calculators. All right, so if you are in class and you are starting here on the home page of your Inspire calculator, the first thing you're going to pick is lists and spreadsheets, and that's this icon right in the middle. And it says, as you hover over, it tells you what it is. And then you're going to want to label your columns. The A column we're going to label as X, and the B column we're going to label as Y. And since I already practiced and entered this data, it automatically populated, but you will need to type in the data into the table. Once you have your data in the table, you're going to go back home. And you're going to select Data and Statistics, which is the next icon, and it will bring up all of your data in this scattered array of points in kind of a grid that has not really been defined yet. So we want to click to add variables to our axes. So the bottom axis, we're going to call that X. So find your X, and it will scatter your data according to the X values. And then along the Y axis, we'll add Y. We can clearly see the decay, the decrease in the number of bacteria over time. Okay, so now we are ready to go to menu. We select option 4, which is analyze, option 6, which is regression, and we want an show exponential, which is option 8, and it gives us our equation. So let me move this over. So I'm going to go ahead and write this down. Y equals 2746.61 times 0.829756 to the power of x. So that's what I've written down in part B. Now I want to demonstrate how you could accomplish the same thing using a Desmos calculator. Maybe you don't have access to this calculator at home. So using Desmos is actually even easier. So you go to desmos.com/calculator to pull up the graphing calculator. The first thing you're going to click is this plus sign, Add Table. And then you'll enter the data. So in the X column, I have 1, 2, 3, 4, 5, 6. And then in the Y column, I have 2157, 1802, 1698, 1429, 1130, and 800. So you can see the points graph here on the graphing feature. Now I go to the next line, and I'm going to type in Y1, and then I'm going to type in a tilde, and then A times B to the power of X. And I just used my caret key to get my exponent, X1. Okay. So here you see it's given me an exponential regression. And it tells me the A value, and you'll see that it's a little different than what I got when I did the Inspire. So I'm going to write this down as well so you can see Y equals 2598.65 times 0.845692 to the power of X. So it's just a little bit different, just based off of the processes that the two calculators use. But they are very, very close. The next question on our paper says, how many bacteria will be present at the end of 10 days? Now remember, our X values were the days. So I could pull up just a regular old calculator, Desmos scientific calculator. I can use my function that I just found and substitute 10 in place of X. If I used my first equation, 2746.61 times 0.829756 to the power of 10, then I get approximately 425 bacteria. I wonder what I would get if I used the equation that the Desmos calculator gave me. 2598.65 times 0.845692 to the power of 10. The number is a little different, but still pretty close. So that's why what we have is an exponential regression. It is just the best that our calculator can do. So while the numbers are a little different based off of the calculator that you used, they're still pretty close. Now it says, will the bacteria ever be completely gone from the culture dish? Explain why or why not using your knowledge of the graphs of exponential functions. So I'm going to go back to this graph. If you think about the horizontal asymptote here, since we are not adding anything to the end, the horizontal asymptote is y equals 0, or the x-axis. That means that as this graph continues, and I can kind of click and drag it, you can see that while the graph continues to get closer and closer to the x-axis. It's never actually going to touch the x-axis. So theoretically, the bacteria will never reach zero. So back here to my paper, will the bacteria ever be completely gone from the culture dish? Theoretically, no. Because the horizontal asymptote is y equals 0, and the function will never reach this value. It will approach this value, it will get really close, but theoretically it will never actually equal 0.